So in a partial ordering relation, there is an ordering among the elements of the set. Okay, so between sum of the elements, there is an order. Like for example, if my set is, let's say, 1, 2, 3, 4, 5, 6, 7, if this is what my set is, and the relation defined on set S is a partial order relation, if we define any other relation on the set, that is a partial order relation. This is not less than equal to as per se, means as per that 1 is less than 2, not in that sense. This less than equal to the symbol for partial order relation. Let me just write it as R. Okay, let me just write it as R and say that this R is a partial order relation. This R on set S is a partial order relation. Then what a partial order relation on a set does is, to some elements of the set, there will be an ordering. Okay, and they will be involved in, means those elements are guaranteed to be in one disconnected, one connected component of your Hasse diagram. Like for example, maybe your Hasse diagram is 1, 2, 3, 4, 5, 6, and 7. Maybe this is your Hasse diagram. So there are 3 connected components of your Hasse diagram. But then the elements that have an ordering among them, they are guaranteed to be in one connected component. So 6 and 7, they are just isolated vertices here. So they are not in ordering with anybody else. But if you look at 1 and 2, there is an order between 1 and 2. There is an order between 1 and 3. That is, 1 is related to 3. There is an order between 1, 2 and 3. Okay, and that order is 1 is related to 2 and 2 is related to 3. There is an order between 1, 3 and 5. And that order is 1 is related to 3 and 1 is related to 5. And the order is 1, 3 and 5. Right. Now what I am trying to say is, in this video, what we are looking at is, given a Hasse diagram, find out all the elements that have an ordering among them. So if I have to find out all the elements that have an ordering among them, so we will find that there are, how do we find it? So actually what you will do is, for any given component, you start from the minimal element. So I start from 1. Now 1, and go in the upward direction. So 1 to 2. There is only one way. There is only one way to go in the upward direction. From 1, there is only one edge outgoing. So 1 and 2. Now, but from 2, you have 2 edges outgoing. 2 edges outgoing. This will give you 2 sets. In one of the set, you will have 1, 2, 3, and in another set, you will have 1, 2, 4. Why? Because 3 and 4, they are incomparable. If you see, the moment you see you are diverging in 2 different directions, or when you are diverging in more than one direction in the upward direction, those will give you another set. Okay. Similarly, from 3 you go to 5. So this is one set of elements that have an ordering among them. So 1, 2, 3, 5 have an ordering among them. Similarly, 1, 2, and 4 have an ordering among them. Similarly, just start with 6 and that's it, and 7. So if the question is, what are the set of elements, give the all set of elements that have an ordering among them, then this is what you will give. Okay. So clearly what is the takeaway is that for elements that are in the 2 different connected components, those elements definitely are incomparable, and so there is no ordering among them. For the elements that are in the same component, if they are comparable, then there is an ordering. If they are incomparable, there is no ordering. So for example, you can see 3 and 4, they are incomparable, so they cannot be in one set. 3 and 4 are in different set. Similarly, 5 and 4, they are incomparable. They are in different sets. Okay. And how do you give it in a bottom up manner? How do you give these sets? It's very simple. Every time you see there is a divergence in multiple direction in the upward way, it means that for each direction you are taking them in one set. Because with each direction, what you are guaranteeing is that from 3 you are not going to get an upward path to 4. Okay. See, from 2 you are going to 3, and from 2 you are going to 4. Of course, if you have to reach 4 from 3, you cannot have an upward path. Okay, the another scenario would be like this. What if you have not 4 like this, but you have 4 like this? Means I am taking another case. Let me draw another one. What if I have 4 like from, okay, just a minute. What if my another relation R, this is R1, let's say S comma R2 is also a partial order relation, and the Halsey diagram is like this. You have 1 and then 2 and then 3, and now from 3 you can go to 5 in one way and 4 in another way, and 6 and 7. Then what are the elements that have an ordering among them? Now if you see 3 and 4 are comparable, so they will be in one set, no doubt about it. But now your sets will be 1 1 2 2 3, but from 3 there is two ways. From 3 there is a divergence, so you can have 5 here, and 1 2 3 and 4, and then 6 and 7. Okay. Okay, before I take another example, I want to make it clear one more thing. If you look at the non-reflexive pairs for a given set, for a given set, their non-reflexive pairs would be 1 and 2, and there is one ordering, 1 and 2, and then 2 and 3, and then 3 and 5. These are the reflexive pairs. There is no other pair that is possible. Okay. So what are the ordered pairs because of this set? What are the non-reflexive? What are the non-reflexive pairs that are because of this set? In your partial order relation, because of this set, what are the non-reflexive pairs? So you know the order. What is the ordering? Ordering is 1, then 2, and then 4. Then what is the non-reflexive pairs? The non-reflexive pairs are 1 2, 1 4, and 2 4. Okay. Similarly, if this set is given to you, that the elements of this set has an ordering among them, what are the non-reflexive pairs that they contribute to your partial order relation? How do you find it? First you need to know the ordering. So ordering is 1 2 3 5, 1 2 3 5. This is the ordering. So the non-reflexive pairs that they contribute is 1 and 2, 1 and 3, 1 and 5, 2 and 3, 2 and 5, 3 and 5. Okay. So that's what I try to. So this is what I wanted to cover in this video. Note that so far in all the videos about partial ordering relation that we have covered, mostly and most certainly almost always, I have talked about posets that are finite posets. So I have not considered a scenario, I don't think any scenario so far, where I am talking about the infinite poset. So in coming videos, we will deal with infinite posets also. So For example, if in the summary video of maximal and minimal elements, if you can recollect, if you have watched that video, so as you can see in your in the video on the summary of maximal elements, minimal elements also, what we took is a set of n elements. So it was a finite set, okay, and we talk about how the smallest possible partial order relation is a reflexive relation, and and in it you have maximum number of maximal elements or minimal elements, which is equal to nothing but all the elements are maximal and minimal only. But then as you add non-reflexive pairs, okay, the moment you add non-reflexive pairs, the number of maximal elements and minimal elements may decrease, and ultimately if you have enough non-reflexive pairs, then you will find that the number of maximal or minimal elements will decrease to 1, and it becomes a unique maximal and unique minimal. When it is unique maximal, unique minimal in a finite poset, then there are greatest and lowest element. All of these things we have seen. That is for the finite poset. We considered a poset relationship on a finite set. Now maybe in upcoming videos, I don't think in the next video, or I don't have a plan right now, maybe more things are to be added here, but when we will see infinite poset again, and then at last we will summarize everything, and then we will summarize partial order relation and partial order relation versus equivalence relation, and then we will finally start with lattice. I think I will be able to complete set theory in next 10 or 15 at max 10 to 15 videos. Thank you very much.